All right, party people. Here we are. YouTube channel is created. I have way too much free time and I'm haunted by thinking about science way too often. So I'm gonna offload some of my delusions onto the web for everyone to enjoy. No need to thank me. So, keeping it calm, starting kind of easy, talking about why electrons don't fall into the nucleus. So this is a cool example, I guess, of spoiler alert. We need to talk about some quantum mechanics. And personally, I enjoy quantum mechanics conceptually. Once you, okay, I'm not great at physics. I just know enough to get by. But once you start doing the math of quantum mechanics, it gets a little bit burly and kind of scary. But luckily, in this video, you don't really need to know that much math. So hopefully it's easy to follow along. But yeah, talking about why electrons don't fall into the nucleus, which if you think about classical mechanics, which tells us that opposite charges attract, if you're thinking about, let's just say for simplicity's sake, the hydrogen atom, you have one proton and one electron, and they're opposite charges, so they should be attracted. And you would also think, based on classical mechanics, the electrons are going to orbit, but then run out of energy at some point, and it should just land and be chilling with the proton, but that's not what happens. So what does that mean? Classical mechanics is not good enough. And that is where we have to wait until early to mid 20th century, where we have a bunch of physicists laying the groundwork for quantum mechanics. So like Niels Bohr, Erwin Schrödinger, Max Planck, Paul Dirac. But who I'm going to talk about today is Werner Heisenberg. And this equation that he created is called the uncertainty principle. So essentially, the way I think about the uncertainty principle, I'm going to preface this just because I find the answer to why an electron doesn't fall in kind of unsatisfactory. And I think one of the reasons why is that the uncertainty principle, and correct me if I'm wrong, I find it very similar to the theory of gravity in the sense that we have Newtonian gravitation, then Einstein added on top of that. We have equations that model how gravity can work and how it does work, the force that it exerts on us and everything. And they work really well with observation, but there still isn't an underlying why is gravity a thing, you know? And it's very similar in the case of the uncertainty principle, where we know in a lot of scenarios that this equation holds up, it passes the sniff test, it works and is useful in a lot of cases, but it isn't really sure why. Okay, so we're going to talk about the Heisenberg uncertainty principle, which I have right here. So as I said, we have this uncertainty in momentum, an uncertainty in position, and that's all going to be greater than or equal to h over 4 pi, which is just a constant that I've written here. That's its value. And so let's think about this equation if it can be used in a macro scale. So imagine I know my momentum. Is that going to mean that I know less about my position? That's what this equation is claiming. So I weigh a whole 77 kilograms, and let's say I'm moving at 1 meter per second. That means my momentum is going to be 77 kilograms per meter per second. And we plug this in here into P so we can find the uncertainty in X. So what we find is my uncertainty in position is going to be 6.85 times 10 to the negative 37 meters. So for context, the width of a hydrogen nucleus, as you can see here, is 1.7 times 10 to the negative 15th meters. So what this is saying is if you saw me on a power walk, or however fast 1 meter per second is, if you saw me walking at that speed, based on the uncertainty principle, it's saying that you would see me walking, and like you would see me walking, obviously, oh my god. But you're gonna see me walking, but then my uncertainty in position means you're gonna be unsure if I'm 6.85 times 10 to the negative 37 meters too fast or ahead. If I'm that, okay, this is getting stupid. What I'm trying to say is the uncertainty principle does not work for macro cases, or it does, but it's just irrelevant. We're too big for the uncertainty principle to care about us. But when you start using the uncertainty principle, thinking about small particles, we can set it up such as we're setting up the uncertainty in position so that it's the width of a proton or the nuclei of hydrogen, right? And we get some uncertainty and momentum out, and we can plug in the weight of an electron to see how fast it would be moving if it was confined to a space the size of a proton. And what we find is that this electron will be moving at 100 times, more than 100 times the speed of light. And this is kind of concerning because something that Einstein worked really hard to conclude is that the speed of light is the max. There is no more than the speed of light. So that's really weird, right? So let's look at a graph that might give us a better idea as to why electrons won't fall into the nucleus. Here's a potential energy graph, also showing the distance of the electron from the nucleus. And in this case, potential energy is just being measured as the charge of these two particles times some constant over their distance, right? So if you have an electron that's not near a nucleus, it won't feel any force. And then once it gets close enough, it starts feeling this force, and it metaphorically tumbles down this well. And it gets stuck at this lowest energy level where it's most stable at. And visually depicted, what you can see is once you get too close to a nucleus, then there starts this exponential increase that just keeps going towards infinity of the amount of energy that you get, that the electron would have by being too close to the nucleus. So here I have, this is not to scale, by the way, I'm just kind of eyeballing all of this. Here's the width of a proton. So I'm trying to show graphically here, just like there would have to be a crazy amount of energy for you to have an electron near a proton. So much, in fact, that is shown to us by the uncertainty principle that it is not possible to have an electron be near a proton. And that's kind of the unsatisfying answer, but that's, I guess, all that we can conclude so far, since we don't understand really why the uncertainty principle works the way it does. And we can also talk about orbitals and all that type of stuff, but just on a surface level, one of the reasons we know electrons won't fall into the nucleus is because of the uncertainty principle. And I guess that's that, right? I've answered the question kind of okay, I guess. But since we're here, bonus question, I bet you didn't see that coming. I'm just going to talk about the uncertainty principle as it relates to protons, and more specifically, the quarks that make up a proton. So a proton is made up of 3 quarks. Every, particle is made up of quarks. Every proton is going to be made up of 2 up quarks, 1 down quark. Electron is going to be made up of some quarks. I don't know the combination. Anyway, there comes a problem though when we think about the mass of these quarks on their own, right? And if we add this together to get the mass of a proton, it's roughly 100 times less than what we see from the measured weight of a proton, right? So we know that these quarks are gonna have to be, the uncertainty in their position is gonna be the width of a proton, because obviously these quarks are inside the proton. So we get this uncertainty in momentum, and from that, if we know that these 3 quarks, this is, I think gluons are all supposed to be in there, but let's just assume for simplicity's sake, all the subatomic particles you need to compose of a proton, mainly being those 3 quarks, the 2 up, 1 down, is going to weigh 1.59 times 10 to the negative 29th kilograms. And in order, the velocity that they need to be moving at in order to, be in that small of a space would be 6.5 times the speed of light, right? Which is really confusing. Why is it that quarks do not add up to the weight of a proton, right? And they need to be moving at crazy high speeds to achieve that. And one thing that we didn't take into account is relativity. And this is the missing link when it comes to how quarks get their mass. And this is something that Einstein found, is that mass is highly dependent on whether or not you're next to something really, really big or going really, really fast. So in this case, we have this equation here that's essentially stating this is your velocity here, and it's going to be over the speed of light. So let's just say, imagine you're moving at just 1 meter per second, right? It's going to be 1 squared over the speed of light. It's going to be some unimaginably small number. This is basically going to cancel out to be just 1, and your mass at rest is going to be your mass at relative, or that's going to be your relative mass. Since you're not moving fast, your mass at rest is going to be essentially the same as when you're moving. But in the case of these quarks, we can think about the mass at rest is going to be them when they're not moving. So we know that they all weigh that collective total combined, and that a proton should weigh this much, right? So what we can do is we can find the velocity they're going, so that the quarks, when they go fast enough, they're gonna get extra mass from that crazy speed they're going. And what we find is that v is equal, or their velocity of the quarks is roughly equal to 0.99995% the speed of light. And that is just kind of crazy. Alright, so we are at the end of the video. I hope that what I talked about was marginally informative. If not, that's kind of embarrassing, and I'm sorry. But yeah, I think in the future, going into the future, less of my videos are going to be this math heavy. I think this was just probably one of the cooler ideas I had for a video, so I just pounced on this one first. I don't really have a schedule or anything, so videos will come out when I feel like it. If that is in the near future at all, it's probably as certain as my momentum when I know exactly where I'm sitting. Am I right? So, great video, guys. Hope you enjoy.